Welcome to the tutorial about Nusensi, NuGrid sensitivity tool, which allows to perform single-zone nucleosynthesis calculations with BPN in parallel, and which allows to derive the sensitivity factors of abundances calculated, and which are derived either from decayed or undecayed species. In the first part of this tutorial, I will demonstrate the method to do those single-zone calculations, and in the second part I will focus on the calculation of the sensitivity factors by using Nusensi's Python tools. Of course, first of all, PPN has to be downloaded, and in this tutorial I use PPN revision 5916, which you can see here with its 3 packages, but I have also downloaded Nusensi, which you can download by using the svn command here to the NuGrid svn tree. Nusensi consists of 3 major parts. First, the jobs directory, from which you launch the PPN jobs and do some modifications. In the second part, the run template, you add your PPN run directory you want to test, want to do your tests with, and in the third part, the analysis tier, you can do the analysis, the sensitivity calculations. Note that in all those 3 directories you have your README file, which explains step by step what you have to do. First of all, we start in the run template directory, which has a source template, and as you can see, source template basically is the PPN run directory, except that there is an additional file, run_sense.sh, which has to be there, and when you want to prepare your own PPN directory, you have to add run_sense.sh. But before we can start compiling this run directory to create our executable, we have to make sure that in run template np data, the np data directory, is set properly. And np data in here is empty, it's just a replacement, and so I will delete it, and you have to link it to your np data directory you created in your PPN version, version downloaded. And I will just use a link here to my PPN version to np data and add it to the run template directory. And in the next step, we have to make sure that that actually the run directory is properly set up. As a first step, it's necessary to set ppndir to the directory where your PPN is stored. Furthermore, it is necessary to add and modify the make local, which is part of the PPN directory. It is in PPN and then code make local, and you're supposed to choose different make locals depending on your system. And in my case, I have prepared make local already and set also here the PPN variable to the same path as I did in the config.sh to my PPN version. And now after we made sure that all the variables are properly set, we can start compiling the code the run directory, and we will produce our ppn.exe, which will then be used later on for those runs. Now, Nusensi is essentially modifying rates, because we want to do tests with rates, and the modification is done through a file the rate modification called network Setuptxt, which is here. It basically contains all the species and all the reaction rates relevant for the nucleosynthesis calculation. And in order to create network Setuptxt, for our purpose, we have to start ppn, but with a special setup. Here I said ininet equals 1, and with this modification I can now start the run, and it will just do a calculation. I will just set up the network and produces the network Setuptxt, and then it will stop. And this is a very short step, but it is necessary for Nusensi. Now we have to do another modification, again of ppn physics.input, and set ininet to 3, which allows the code then to look into the network Setuptxt and read from this file. Now we've finished setting up the run template directory. We can directly go to jobs, the jobs directory. And the most important file in the jobs directory is called nusensi.input. And at the beginning you have to set important variables to tell the code where should it put the simulations and the run directories. And for example here, where should the results be stored. And with the results I mean certain files which are produced during the run. I will talk about those files in a minute. Then furthermore you have to set the variable ini_rates, which allows basically to run Nusensi in different modes. For example, if we start with ini_rates equals 0, we can make use of those 3 variables here, for which which are basically defining here the size of the network, so the size of the reactions which you want to modify. In this case I want to modify reaction number 229 and 230, and I want to change them by a factor 100, so by a factor 100 down. And for this purpose now we can just write it and then execute the script Nusensi, and by using RunSssh. And what it will do basically, it will create a file called RunList.txt. It just creates this file, it does nothing else. And the file contains basically lines which start with run underscore and then the rate which is supposed to be which will be changed, and then the factor of this rate change. So in this case a factor of 100 for both cases. But no ppn run has started yet. In order to start the calculations we need to open Nusensi again, and we need to set the ini_rates to 1. And now it will ignore this output here. And interesting for the actual calculation is this output part here, where you can specify 1 or more cycles, which tell Nusensi how far the ppn calculations should go. For example, here I specify until cycle 125 for the carbon-13 pocket example, and the code will then stop the runs at when the file or files related to cycle 125 are created. But one can also, for example, look at the RunList example, which is available in Nusensi. Here with a different which contains 2 different rates. two different runs, rate 44 and rate 45. And now I have to answer the question, what is that ID of the rate? It is, or you can figure this out by looking in run template and then source template and have a look at the network Setuptxt. And as you see here, for the rates stored in network Setuptxt, there's always an ID at the beginning, a number. And now if I look at the 44 I had before, I can identify the actual rate. So it's carbon 12 plus an alpha, and then emits a gamma. And so it's carbon 12 alpha gamma, and then 45 is carbon 13 alpha n, so the neutron source in the carbon 13 pocket. And so we can use RunList txt example and copy it basically to the RunList txt, and then we could do the same execution as before. We start run.sh and start those two runs, ppn runs, with those modifications specified in RunList txt. And before I do that, I would like to demonstrate the ability of Nusensi to do those parallel calculations on different machines. And here you have the machines file. Each of those two lines here contain as a first entry the name of the server which you want to include and address, and the second part is the number of processors you want to use in your ppn calculation or calculations. Each ppn calculation needs only one processor. So essentially I have defined here on the server Digu I want to use one processor, on the gerbil I want to use also one processor. In total I can do 2 ppn runs in parallel, and that's necessary for our 2 runs specified here in RunList. So I expect that the first and the second run will run on Digu and on gerbil. On each server, 1 run. Of course, you can specify in the machines file more server, and you can add more processors, and can run then more ppn runs in parallel. Let us now start the calculations of those 2 runs, and have a look what's happening. Here we access the machine Digu and the machine gerbil, and now the program waits until the ppn runs finished. And I access Digu and gerbil, and here I'm in this window on Digu, and I just want to check if ppn.exe has started already. So I would do top and then grab ppn.exe. This might be enough. And you see here in this line that our ppn.exe, so 1 ppn run has started on Digu, and we can use the same line of course on gerbil. The other server I've specified start the same, and as you can see ppn.exe is also running here. And you can wait until basically this program here is finished, which then tells you that all your runs successfully finished. Okay, so the reference run is finished. As you can see, we have created all those files, the .dat files, until cycle 125. On the other hand, our runs submitted here are finished, and we can, for example, look at the results in our result directory. And you see here the results for the 2 runs, and we can look at them. example 45. This is the carbon-13 alpha N reaction. And you see we got only one file in here, on one isomass F file, and the isotope database and the runinfo.txt. And runinfo.txt contains the name of the rate we have changed, modified in this run, which is quite handy because it's some sort of check. And so here we modified the carbon-13 alpha N reaction. And the reason why there is just the isomass F125 is because we have specified in our Nusensi input in the end here that we are only interested in the dat file 125. But you can just add more names here, more cycles. For example, cycle 15. On the other hand, we can also have a look at the simulations directory, where the runs were performed, and we have two different directories depending on the names that depend on which server we have used. We have used Dego and Gerbil, and so we can look in RunSssh, where you find here the run directory, and in RunSssh, where you see the other run. These are full run directories. Now, after performing those calculations, we can finally calculate sensitivity factors. And for that purpose, we go into the analysis directory, and it contains, again, contains a README file, but also as the main Python tool here, the sensitivity.py. And I will start a Python session here. I use mpython, which is an alias for IPython pylab -- profile numpy. And with that, I can now import the sensitivity file by using import sensitivity as sense. And now the sense contains my module. And I can, in the next step, for example, have a look what is sense actually doing. What are the steps I have to perform? And in this case, I have to start first by reading in the reference run, specifying the cycle number I'm interested in, which is 125, and then the path to the reference run. And as you remember, I have done here the reference calculation, and so I just specify this path. And in the next step, I can already calculate my sensitivity matrix by using the function sense_matrix. And there are a couple of input parameters you have to specify, and others are optional. In this case, I read in first the results in the result directory, specified here, and then the network size, the number of rates basically, and we used rate 44 to rate 45, and in total we used a factor of 50. And those values here, these were the ones we also specified in the nusensi.input file in the jobs directory. Furthermore, you can define if you want to analyze the decayed abundances of your runs or the undecayed. In this case, I look at the undecayed, so on all species, and then I define the name of the sensitivity matrix file, and then I execute it. And the function has now generated the sensitivity matrix file. And you see on the columns the number of isotopes, the abundance given by the reference run. Okay, this is the final abundance. And then here you see the sensitivity factors for those two rates we were looking at, carbon-12 alpha gamma and carbon-13 alpha n. And it goes all the way through all the unstable species. And that's basically, these are the sensitivity factors. And to figure out more in detail what all those parameters mean, you can always use a question mark behind the function, for example in this case, and you can read through a documentation here explaining the structure and the input parameter. Now, as addition, if needed, you can calculate the errors of the sensitivity factors. And for that purpose, you have to use another function called error matrix, where you specify the name of the sensitivity matrix, the one we just created basically, and then the output name. I call it error sensitivity matrix, the abundance threshold of species of interest, so everything below 2 × 10⁻15 will be ignored, all those species with those abundances. And then I also specify a sensitivity threshold, because I might be interested only in species of a certain sensitivity. And then I execute it, and here we go. We can look at our error sensitivity matrix. And it looks almost the same as the sensitivity matrix, except that you have behind those sensitivities a factor. In this case, you don't have any, and here you have a percentage of error. And so the way how you calculate those errors is explained in the functions. But what is needed for that, of course, are the errors coming from the rates. And in this case, we look at 2 rates, carbon 12 and carbon 13 alpha and alpha gamma. And so in this case here, you can see there is no error because carbon 12 alpha gamma was not specified. The error of carbon 12 alpha gamma was not specified. And all those errors have to be specified in the file called error.txt, which is here, where you have the name of the reactions, and then the error and the relative error. And now we can look. We have, for example, for carbon 13 and gamma alpha n here, error of 4%. And that is it. That's the tutorial. If you have any questions to that, what I've explained, send me an email at critter@uvic.ca. I'm happy to hear any sorts of questions, comments, and I'm happy that you went through this tutorial, and I hope it's helpful for you. Thank you.